another episode of Mathmatical Mayhem. Today we will be looking into how simple integration can help stuntmen achieve their goal of landing a jump safely with the help of a mechanical engineer. First, let's take a look at some footage of a stuntman attempting
The
a
flight
jump.
over the distance, however, was flawless. But because of the slower speed, he remained short on the runway,
Tim, mechanical engineer, here to explain the stuntman's intended velocity, what integration is, and how integration as a mathematical technique is used to calculate independent and dependent variable.
249 feet was the distance. We calculate that to be 76 meters in metric, and then we solve that to be in terms of t using this formula here, which is a basic engineering or physics formula. So we simultaneously solve that with it in its x and y components to come down here to give us our v value. So we solve that in terms of v, keeping that throughout, and gives us 29.34 meters per second, which equates to 105.62 kilometers an hour. Now that's the ideal speed. Now we calculate for the bike to land 1 meter short, the speed that he would have had to go would have been down here at 29.15 because we calculate here 75 meters rather than 76. And that just follows through and gives us this result. So using our calculated velocity values, we're using the technique of integration to work out our acceleration. Well, our acceleration is given using a linear formula for the bike. And using that, we are able to integrate that and find our velocity and our displacement for the bike. Now, that's given by these formulas here, where the dependent variable is the velocity and the independent being the time, or in this circumstance, the displacement being the dependent variable and then the independent variable being time as well. So we calculate using our acceleration formula down, keeping t as our independent variable. And we sub in our values for v, and that gives us 8.725 for the approximate time for the run-up for the bike to accelerate at this speed. And we take that down and we sub that in to the displacement formula, and that gives us 72.64 meters of displacement the bike is needed over here to do that. For the bike to land 1 meter short, we simply just sub in 29.15 rather than 29.34, which is what the bike would approximately have been going to land 1 meter short. We sub that down with the quadratic formula, that gives us 8.7 seconds of acceleration time. Now, subbing that in as our limit of integration, that now gives us 71.91 meters once it's integrated. As my colleague Zeb will explain, the difference in the run-up is fairly significant in the scheme of things, as seen in the video.
As you can see, the change in displacement is just our two values. This value here is our ideal displacement that we worked out. Then we just minus the value for approximating if it was about 1 meter short. And so we get 0.73 meters, which is, you can round it up or whatever. But as you can see, it's not very much distance, this value, but it's very important because it could mean the difference between life and death. So, and as a summary, with our run-up of 72.64 meters, it takes 8.7 seconds and we get 76 meters clearance, as opposed to a 1 meter short run-up, or 0.73 short run-up, sorry. It'll only take 8.7 seconds, which is very close values, like they're very similar. And so then we'll get 75 meter clearance. And this diagram just explains it a bit more in simple terms.
Back to you, Cassandra.
Thank you, Tim and Zeb, for that interesting analysis of integration. This just goes to show you that even the simple maths is important in everyday life. Now stay tuned for another episode of Mathmatical Mayhem!